Okay, today's lesson is about Hess's law. Before we do that, I want to talk about the difference between enthalpy or energy and enthalpy. Now, energy is a very broad term, and it can describe a lot of things in terms of chemistry. It can be talked about the potential energy, which we think about which is stored in bonds, or it can talk about the kinetic energy, which is the actual molecular movement. Now, all these things are true for enthalpy. Okay, but the definition adds a lot more. It also includes It takes into account all the pressure and volume that's included within a system. Now, a way to picture this is we're going to draw here our calorimeter. In the center here, I'm going to have my reaction. Now, we established in previous lessons, we can't measure the reaction. We can only measure the surroundings. Now, in order to do that, we measure it with the temperature. So we put in our thermometer and we measure the surroundings. So when we're measuring this, what we're actually measuring is Q. And we're using the Q, the calorimeter, is equal to MCAT. Now, what are we measuring? In this particular case, we are measuring heat energy. So we're not directly measuring the reaction, we're measuring the heat given off to the surroundings. So because of that, we know over here that the heat, the calorimeter, so basically the energy that's given off at the calorimeter is equal to negative Q, the reaction. Basically, if the water is warming up, the reaction is losing energy. If the water is cooling down, the reaction is gaining energy. Now, the problem with this is that Q is very specifically referring to heat. Okay? So the problem is within the reaction, we're not necessarily going to have heat. Remember, we've talked about it's being stored in bonds in terms of potential energy, kinetic energy. So when we're talking about the Q of a reaction, that's not really the appropriate terminology we would want to use. We want to use delta H, enthalpy. Okay? So the advantage of using this as our enthalpy is that this basically redefines and expands our definition of what energy can be. It doesn't just have to be heat energy like it was with our surroundings. It can include kinetic energy and can include potential energy. So the purpose of Hess's law is we're trying to figure out how much energy it takes to make or break bonds. So Hess's law basically states that if you're looking at a reaction, it doesn't matter how we get from our reactants to our products. The only thing that matters, it doesn't matter what pathway we take, it's independent. So if we look at this, for example, we're going to look at carbon dioxide. In this example right here with my red pen, we're saying, well, if we had solid carbon and we had oxygen and we put energy into the system, the result is that we're going to get carbon dioxide gas. So why is this value here to be negative? Why is it negative 393.5? Well, because we're creating bonds. If we're creating bonds, that means we're storing energy. The other way we could look at it, and I'll show it with the blue pen, is what if instead, in order to make a carbon dioxide, it took two reactions? We took carbon and oxygen, turns into carbon dioxide and oxygen. And from there, we can take that oxygen, add it in, and make it carbon dioxide gas. In this particular case, my blue is 2 steps. But at the end of the day, the energy it requires is still going to have to be the same. So if this step was 283, and overall, the total H is 393.5, this has to be negative 110.5 kilojoules. So what we're saying up here is that when we've got a chemical reaction, it can be written as a sum of 2 or more steps. Okay? The overall equation is going to equal the sum of the individual steps. So let's picture it one more way. So for example, we're going to have this one reaction here where carbon and oxygen turn into carbon dioxide gas. Now, we established in the previous step this is going to be a negative delta H of 393.5. Alternatively, for reaction 2, where we instead assume of this being a one-step process, we assume it's a two-step process. Our first step with carbon and oxygen produces carbon monoxide and half an oxygen molecule. It requires this much energy, negative 110.5. Our second step will be carbon monoxide and oxygen turns into carbon dioxide gas. This will require even more energy to attach that second oxygen. If you add this up, the delta H will be negative 393.5 kilojoules. Now, where on earth am I getting these numbers from? I'm looking them up. So on your test, you're going to be able to look at the table of these values up because they're well established. Okay, so for our first example, working with Hess's law, we're going to be looking at the equation here that I've outlined in black. Now what this is talking about is carbon solid reacting with water vapor to form carbon monoxide gas and hydrogen in the following reaction. Now there's no such thing as this reaction occurring in one step. It's actually a three-step process. Now we know the enthalpies because they're standard values. We can look them up. They've been researched over and over again. So we know what their values are of kilojoule per mole. So these are our three reactions. Now these three combined in some form or another is going to equal this reaction we've got up here. So how does it do that? Well, let's see what we can do. We know for starters that carbon's going to be on the left-hand side. Because carbon's going to be on the left-hand side, this reaction here also has carbon on the left side, so we can simply just write it out. So carbon solid plus O2 gas turns into CO2 gas. And we know in this case our delta H is equal to negative 393 kilojoules. So we're happy because we've got a carbon on the left side. But if you take a look, we don't have carbon dioxide anywhere here on the right side. So what we're going to have to do for this next one is we're going to look at this equation right here. We can see we've got carbon dioxide. It's on the right side. Now what we're going to do is we're going to take this reaction and we're going to reverse it. Because basically what we need to do is we need to take this carbon dioxide and we need to break its bonds apart. We need its individual elements to make different things. Like, for example, carbon monoxide. So we're going to write this reaction backwards. So CO2 gas turns into CO gas plus 1/2 O2. So if it takes 283 kilojoules per mole to form it, when we break those bonds, as we have here, the value becomes positive because we're releasing that energy. So it's no longer negative 283, it's positive 283 kilojoules. Now let's take a look what we've got. So we now have carbon monoxide is going to be on the right side, carbon's going to be on the right side. We need water on the left-hand side. In order to do that, we are going to use this equation right here. Now yet again, because water's on the right side on this one, we're going to have to reverse it. So it's going to become H2O turns into 1/2 O2 gas plus hydrogen gas. Now because we reverse it, it's no longer negative 242, it is positive 242. So now what we can do is we can start to add it up and see if this all works out. So if we've got carbon dioxide on the left side and carbon dioxide on the right side, quite simply, we can cancel those out. Now we've got oxygen here on the left side. And we've got half a molecule of oxygen gas here and half a molecule of oxygen gas here. Those three things can all cancel themselves out. What we end up with is we end up with carbon solid plus water, gas, turning into carbon monoxide gas plus hydrogen gas. Now if we can add up the equations using symbols, we can also add it up mathematically. So if we pull out our calculators, and what we're going to do is we're going to add up these three values. So in this case, negative 393 plus 283 plus 242. we end up with a value with a delta H of equal to plus 132 kilojoules per mole. So let's summarize the rules of Hess's law. Hess's law states if you can add up the reactions, you can add up the enthalpies. So as you can see from this previous example, we had to rotate equations back and forwards. You can manipulate equation any way you need to, just like if it was an algebraic equation in math class. But whatever you do to your chemical equation, you need to do the numbers as well. So there's 3 rules. We talked about this on the last slide. We can reverse equations. If we reverse equations, positive numbers become negative and vice versa. We can also put coefficients to either increase or decrease the values based on the number of molecules or moles we need. And that's fine. All you need to do is make sure you multiply or divide by the factor. What do I mean by that? This example might illustrate it a little bit more clearly. So this time what we're going to be doing is we're going to be looking at this equation right here. 2 carbon solid plus hydrogen gas is going to produce ethine, C2H2. What is our enthalpy? So we're given these 3 half reactions. So what can we work with? Well, we can, for starters, know that we need carbon on the left side, but we need 2 of them. This equation only has 1. So therefore what we can do is we can double everything. So 2 carbon plus 2 O2 turns into 2 CO2. Our delta H will be equal to 2 times negative 393.5. Since we now have 2 of these instead of 1, this number also needs to be doubled. So therefore our delta H is going to work out to negative 787 kilojoules per mole. What else do we need to know? We need to get hydrogen gas on the left side. Now from what we have here, we just have a simple hydrogen gas. So in that case, this equation, copying it out perfectly, will probably be fine. So H2 gas plus 1/2 O2 gas turns into H2O. Because nothing's changed, we can just say our delta H is equal to negative 285.8 kilojoules per mole. Now what we need on the right hand side is we need C2H2. So if we take a look at this, we can see that reaction occurs right here. But what we're going to have to do in this case is we're going to have to reverse it. So what we'll end up with is we're going to end up with 2 CO2 gas plus H2O liquid turns into C2H2 gas plus 5/2 O2. And our enthalpy is going to be equal to, not negative because we've reversed it, therefore it needs to be positive, so plus 1299. So let's see how we did. We can see we've got a water on the left and we've got a water on the right. I said that backwards. Let's cross those out. We've got a carbon dioxide on the left. We've got a carbon dioxide on the right. Let's cancel those out. So now we've got 2 oxygens and a half oxygen. Now let's change that because we want to make it a fraction. Let's make it 4/2. 4/2 and 1/2 is going to be equal to 5/2 O2s, which is great because that's going to be able to cancel out with this 5/2 over here. So we now know that we're left with is 2 carbons plus H2 turns into C2H2. So now what we can do is we can look at our 3 enthalpy values to figure out our overall enthalpy. So we've got, in this case, we'll work from the bottom to top. We have 1299.5. We've got that. We're going to subtract 285.8, and then we're going to subtract 787. So therefore our delta H is 226.7 kilojoules per mole.